So let's discuss now problem number 1. This is problem number 1 now. We see a 3-member spin joint frame now. It is connected at D by a pin joint. At A we have a hinge support, at B hinge support, at C also a hinge support. And at D we have a free joint which is carrying loads of 12 kips to the right and 20 kips in the downward direction. Now, AMD, if you remember, it was EA or L square. So L was involved there, and then looking at the nature of displacement, the X coordinates were involved. So we need to find out lengths of the members and then the coordinates also. And similarly was the case with the stiffness coefficient elements also. Now, description first you need to see now in these boxes, this number 1, 2, and 3, these are the element numbers. Horizontal, it is 12 feet. Vertical, BC, it is 9 feet, and AB distance is 18 feet now. So, member 1 length, if you want to find out, we have horizontal and vertical. So, this will become 12 square plus 9 square under the root, which is shown here. It is coming 15 feet. Horizontal member length, which is L2, it is 12 feet, and this AD member, which is member 3, it is coming 21.63. So first we need to find out the member lengths. Next, now we find out the coordinates also, because it was including the coordinates also. So as a first step, what we do, we first identify the unknown joint displacements and compute the values of AD matrix now. Now the joint displacements is a 2 degrees kinematically indeterminate problem. By observation, you can say it is joint D, so horizontal and vertical. Now remember, it is your choice. You select the horizontal displacement to the right positive or to the left positive, your choice. Similarly, vertical, upward or downward, it is your choice. But remember, when you assume those, then it is becoming your positive direction, and onwards, whatever you do, that will be based on the initial assumption now. Those will be your positive directions. Now, D1 corresponding to D1, if we look at the diagram, this 12 kip, so AD1 is becoming 12, so 12 is written here. And D2, if we look at it, is also, this 20 is also in the downward direction, in the direction of D2, so this is 20. If D was in the upward, D2, if this vertical force was in the upward direction, so in that case, then AD2 will become equal to minus 20, because that is opposite to this D2 direction. We need coordinates also, so each joint should be given a coordinates, and that those coordinates will help us now in calculating the member forces and calculating the stiffness coefficient values also. Now origin, it is your choice now which one origin you want to select. So in this case, we have selected joint C now as an origin. So origin means 0, 0, horizontal is 0 and vertical is 0. When we come to joint B now, so horizontal, it is in the same now along the y-axis, so it means horizontal is 0, but vertical is, it was 9 feet now, so it is minus 9. Why minus 9? Because downward direction is our positive. If we are going in the downward direction, that will be positive. We are going against the downward, we are going in the upward direction, so this is minus 9. This AB was 18, but we are going in the upward direction again. So minus 9 minus 18 is equal to minus 27. So at joint A, you see minus 27. Coordinates of this joint D now, horizontally, we are coming to the right. Right is positive and it is 12 feet. So 12 we are writing. And then the vertical, we are going 9 in the opposite direction. So this is minus 9 now. So these are the coordinates of. Let's somebody saying, okay, I'm going to take this B as my origin. So here the coordinates in that case will become 0, 0. The bottom, this joint C will become equal to 0, 9 now. 9, why? Because we are moving in the downward, which is our positive, depending on this D2 now. And joint A coordinates will become equal to 0, minus 18. And here, this joint D coordinates, it will become equal to 12, 0. Somebody is saying, no, I'm going to take start from joint D now as origin. So this will become 0, 0. Joint B coordinates, it will become minus 12 and 0. Minus 12 because we are going now in the leftward direction. So left, which is opposite to the right direction. So it means this will become minus 12 and 0. This C joint, it will become minus 12 and 9. And the joint A coordinates, it will become minus 12 and minus 18. So depending on your system, right, and horizontal and vertical, how you assume your positive, and then depending on the origin, you will have to find out these coordinates accordingly. Next, we give D1 is equal to 1 and D2 is equal to 0. So here that is shown from red, we are stretching it to this green position. Now in member CD, the force produced, it was member 1, so it will become AMD in member 1 due to 1 now. Delta is given in one direction, so the last subscript you see 1 now. This horizontal member was 2, so AMD in 2 due to 1, and this top one diagonal, it was member 3, so AMD 3 due to 1. These are the member forces now. And similarly, you can find out the stiffness coefficients also from this one. So now AMD11 should be equal to what? It should be equal to EA over L1 square times XK minus XJ. And XK minus XJ we have from this previous slide now. So XK minus XJ, how we select the near end, we give it K, and the far end we give J. So K is common at this joint we are giving. So this is K, and this is J joint of member 1. This is J joint of member 2. This is J joint of member 3 now. So for the first member now, when we are calculating its length, already we found it was 15 feet. So it will become EA over 15 square times 12 minus 0. 12 minus 0. So let's see that we have this one. AMD11, it is EA over L square XK minus XA. So EA over L square 12 minus 0. And this is the, now when we run the number, so this is, we have AMD21, it will be EA divided by L2 square. L2 was 12 square and 12 minus 0. AMD31, so it is L3 is now involved here, which was 21.63, so 12 minus 0. This way we find out the AMD matrix. At joint this D, if you see now in stiffness, when we are finding out actions here in the direction of this delta D1 and in the direction of D2 now, that will become S11 and S21. And if you see in this S11 and S21, all these three members are contributing. So we'll be taking the summation of all these three members now. And here we see the basic equation. S11 will be in the direction of D1 due to D1 now. Both are horizontal, so only horizontal is involved. The first now, this number, it is coming from element 1 now. EA over 15 cube 12 minus 0. This is coming from contribution from member 2, and this is coming contribution from member 3 now. You see this is L3, and when we run these numbers, we get this 0.1402. Now 2-1, action in vertical direction and displacement is in the horizontal direction. It is EA over L cube XK minus XJ times YK minus YJ. So EA over, this is member number 1. 12 minus 0. Here also, if you see XK minus J is was 12 minus 0. And YK k minus yj, it is minus 9 minus 0. So for member 1, let's check now this minus 9 and 0. So let me go to the previous one. Now member 1 we are discussing. So here you see yk is minus 9 and yj is 0 now. For member 2, it will be minus 9 and then minus 9 again. So let's see now for member 2 in the stiffness. So here this is member 2 minus 9 and minus 9 now. And EA over L and X is already, you can see from here it is coming. Similarly for member 3 now, minus 9 and minus 27. These are the YK and YJ. You can confirm this. This is minus 9 and minus YJ. So already the equations we said, this is just the matter of now putting their appropriate now these giant coordinates values. So when we run this, so we get the second. The second element of this first column stiffness coefficient matrix. Remember, once we calculated S21, you don't need to find out S12 now. Obviously, it will be the same. But if you want to verify, you can do it. So next, what we do now in the direction of D2, we are sliding it down now. So this K is slided down to this position now. Again, if you see in the stiffness matrix, all the three members are calculated. And here, by the time we start sliding it, member forces will be produced. Again, here now in this bottom one, which was member 1, so this will become AMD1, this will become AMD2, and this will become AMD3. This last subscript 2 is coming from why? Because we are giving displacement now corresponding to D2, which is written here. D2 is equal to 1 and D1 is equal to 0. Now, y is involved, y displacement. So, in calculation of the forces, only y coordinates will be involved. And here you see now the y coordinates. AMD1 to EA over L square. So, yk minus yj. You just plug in all these values accordingly. Similarly, as 1 to if you see, again, we have the same value which is coming here. S22 will be EA over L cube times YK minus YJ, YK minus YJ. For all the members, we have all the three members are contributing. So we just plug in the values here and we calculate. You need to be careful now while putting these values. Minus will come with minus. Right? Don't omit this. This is not the absolute value. This is the with the appropriate sign. Now you will have to put this value. So this is how we calculate the stiffness. So AMDs are known and stiffness values are known. It was a 2 degrees kinematically indeterminate problem. We generated all the 4 stiffness coefficient values. Now rest is now this when we put this in organized form. So this is AMD matrix now, and this is our S matrix. What else we need to solve this problem? This is now the matter of just simple mathematical calculations. So we write the now equilibrium equation. We don't see ADL here. AD is equal to, this is the equation now, S times D now. D will become S inverse times AD. We have these values, just plug in the values. Stiffness matrix already we calculated. This is AD. So these are the unknown giant displacements now. AMD matrix already we have. We multiply this by these known values of giant displacements now, and we get the member forces now. So AM1, which was member 1, it is coming in compression, and the rest of the 2 members, they are in tension. So we put now these member forces on the elements. Here you see bottom one is in compression towards the giant, you see the arrows, and this middle one and the top one, they are in tension, so away from the giant, and you see the magnitudes also. Here to find out the support reactions, what we do, we resolve this diagonal force now into its horizontal and vertical rectangular component. Similarly for the bottom one. So this horizontal 9.58, it will be the support reaction here, 9.5. Vertical here is going to be 0. You can apply the regular checks now. 12 kips, so now see whether this is giving you 12 kips or not. 9.7 to the left, 9.58 to the left, and this 7, so 7.28 plus 12, it is coming 19.28. And here if we add them up, so this is also 9 plus 9 is 18 and 0.5, 0.59. So this is again, this is 19 point something. So close to 20 vertical you see now. So 5.46 and this is 14 points. So this is almost, this is also 20. So 20 is balancing with this one. And all the member forces are labeled, the support reactions are labeled, the forces are shown externally applied force, the system is in equilibrium, so it means we have solved the problem. Rest of the three problems now we will solve quickly now. We know the background. Now you can turn on your mics, and if you have any question, I'll give you time, I'll explain. If you need any clarifications, I'm here. Otherwise, what we do, rest of the class can leave the class now, and those who are having YOC exam today, they should stay. We will be calling them turn by turn to give their YOC exam. So now you can turn on your mic.